And now in this lecture I'll answer two questions. The first question, we find out the radius of this circle, and in the second question we find out the area of this circle using two different methods. So we start with the first question. In the domain we have a circle and triangle, the right triangle ABC. This is angle ABC, this is equals to 90 degrees in its size. Side AB equals to 3 units in its side. Side D equals also to 3, line segment AD also equals to 3 units in its length. This is line segment DC, this is equals to 1 unit in its length. And our test is to find out the radius of this circle. So, first of all, we focus on this common standpoint point C. From this common standpoint point C, we have tangent CE. It is tangent to this circle is point E, and we have also second CA that cuts the circle 2 points D and A. So here we can implement rule 25. I'll repeat quickly rule 25. According to rule 25, if from the common standpoint point P, we draw a tangent PA to the circle that is tangent to the circle is point A, and the second PC that cuts the circle 2 points B and C. Then in this domain the following equation is true, that PA square equals to PB times PC. Again, PA square equals to PB times PC. So can actually implement rule 25 in our drawing. As I already mentioned before, from the common standpoint point C we have tangent CE that is tangent to this circle is point E, and we have also second CA that cuts the circle 2 points D and A. So all the requirements for full 25 are satisfied, and therefore we can implement rule 25 in our drawing. So I write it down. From the common standpoint point point C, we have tangent CE and second CA that cuts the circle at 2 points D and A. So therefore we can implement rule 25 in our drawing. According to rule 25, the following equation will be true, that CE square equals to CD times CA. Again, CE square equals to CD times CA. CE square equals to CD times CA according to rule 25. This equation is the implementation of rule 25 in our drawing. C is the missing side of uniticity, so it is CE square that is equals to CD. CD equals to 1 times CA. CA in total equals to 1 plus 3, that is 4. So in total we should find out that CE square equals to 1 times 4, that is 4. So CE square equals to 4. Here we take a root out of this equation, and we get that CE equals to the square root of 4, that is 2. CE equals to 2 units in its length. Tangent CE is equal to 2 units. This is tangent CE that equals to 2 units in its length. In the next step, we'll implement the Pythagoras theorem on the right triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So I copy the right triangle ABC in a new page, and we will implement on it the Pythagoras theorem. Here by PT is the progression from Pythagoras theorem. Side AB of the rectangle ABC equals to 3 units in itself, according to what is given as the question. Side BC is the missing side. And the hypotenuse AC equals to 3 plus 1, that is 4. So actually, this is the right triangle ABC that comes from the original drawing. This right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. So I write it down. AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16. And it is equal to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, plus BC squared. BC is the missing side, so we leave it as it is. So in total we should know that 16 equals to 9 plus BC squared. Here we subtract 9 from this equation, and we get that 16 minus 9 is 7, equals to BC squared. Here we take a root out of this equation, and we get that the missing side BC is equal to the square root of 7 units in its length. So we should find out that this is the missing side BC, that is equals to square root of 7 units in its length. So what is the length of the missing line segment BE? Line segment BE equals to BC minus EC. Again, B equals to BC minus EC. So I write it down. BE equals to BC minus EC. So B in total equals to BC equals to the square root of 7 units in its length, minus EC equals to 2. So in total we should find out that BE equals to the square root of 7 minus 2 units in its length. This is line segment BE, is equals to square root of 7 minus 2 units in its length. In the next step, we'll join points O and D together by a straight line. Point O is the center of this circle, point E is the point of the circle itself, therefore OE is the radius of this circle. We define the radius of this circle as R, so O equals to R. The radius OE, that is equals to R, the radius OE is drawn to point E, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. In the next step, we will do a construction, that is to say from point O, that is the center of this circle, we will do perpendicular on AB. Here from point O, we will do perpendicular on AB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O inside AB. This point is point N. By doing this construction, if we do the quadrilateral NOEB, inside quadrilateral NOEB we have 1, 2, 3 rectangles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral NOEB we have 4 right angles, and according to rule 5, quadrilateral NOEB is a rectangle. Already known. This is quadrilateral NOBE. It is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle NOEB, side OE must be equal to the opposite side NB, but OE is R, it is the radius of the circle, therefore the opposite side NB must be also equal to R units in its length. Likewise, according to the same rule, in the same rectangle NOEB, side BE must be equal to the opposite side NO, but BE is square root of 7 minus 2, therefore the opposite side NO must be also equal to the square root of 7 minus 2 units in its length. What is the length of the missing 9 segment AN? From the drawing it is very easy to see that AN in total equals to AB minus NB. AN equals to AB minus NB. So it is known AN equals to AB minus NB. So AN in total equals to AB equals to 3 according to what is given as the question, minus NB equals to R. So in total we should find out that AN equals to 3 minus R units in its length. This is 9 segment AN that equals to 3 minus R units in its length. In the next step we join points O and A together by straight line. Point O is the center of the circle, point A is the point on the circle itself, therefore OA is the radius of this circle. This is equals to R according to our definition. In the next step I'll copy the right triangle A and O, the right triangle A and O in a new page, and we will implement the Pythagoras theorem on this right triangle A and O. Here by PT is the progression for Pythagoras theorem. So actually This is the right triangle A and O, that according to the original drawing. This right triangle A and O, according to the Pythagoras theorem, AO squared, that is the square of the hypotenuse, equals to AN squared plus NO squared. So I write it down. AO squared, that is the square of the hypotenuse, is equal to AN squared plus NO squared. AO equals to R, therefore AO squared is R squared, and it is equal to AN squared. AN is 3 minus R, therefore AN squared is 3 minus R squared plus NO squared. NO is square root of 7 minus 2, therefore NO squared is square root of 7 minus 2 squared. So in total we found out that R squared equals to 3 minus R squared plus square root of 7 minus 2 squared. So R squared equals to 3 minus R squared. 3 minus R squared equals to 3 squared, that is 9, plus R squared, minus 2 times 3 times R, that is minus 6R, plus square root of 7 minus 2 squared. Square root of 7 minus 2 squared equals to 0.417 0.417. So in total we found out that R squared equals to 9 plus R squared minus 6R plus 0.417. Here we have R squared on both sides of this equation, so R squared will get cancelled. After we cancel R squared on this side of the equation, we have nothing, that is to say 0. But on the other side of the equation, we have 9 plus 0.17, that is 9.417 minus 6R. Here we let 6R to this equation, and get that 6R equals to 9.417. Here we divide this equation by 6, and finally we get that R equals to 9.417 over 6, and 9.417 over 6 is equal to 0.57 units. So we actually found out that the radius of this circle, that is the radius that we are looking for in this question, is equal to 1.57 units in its length. So we finish with the first question. In the next step, I present to you the second question, and we will solve the second question in 2 different methods. In the second question, our task is to find out the area of this circle. So in the drawing we have a circle. This is line segment BC, that is equal to 6 units in its length. This is chord BA, that is equal to 13 units in its length. This is line segment CD, that is equal to 18 units in its length. This is angle ABC, that is a right angle. This is angle BCD, that is also a right angle. Again, our task is to find out the area of this circle. So first of all, those two angles are defined as one-sided interangles. The sum of those two angles is 90 degrees plus 90 degrees is 180 degrees. And whenever the sum of two one-sided interangles is equal to 180 degrees, then they must be located between parallel lines. That is to say, chord BA is parallel to chord CD, to line segment CD, according to Rule 27. So repeat quickly Rule 27. According to Rule 27, if the sum of two one-sided interangles is equal to 180 degrees, then they are located between parallel lines. In the drawing we have line AB and line AB, line A and line B, and line C that cuts the two lines A and B. Those angles are alpha and beta, and are defined as one-sided interangles. If the sum of those two angles is equal to 180 degrees, that is to say, if alpha plus beta is equal to 180 degrees, then those two angles must be located between parallel lines. That is to say, if alpha plus beta equals to 180 degrees, then line A is parallel to line B. So we can actually implement Rule 27 in our drawing. Why? Because in our drawing, the sum of those two one-sided interangles is equal to 180 degrees, and therefore they are located between parallel lines. That is to say, chord BA is parallel to line segment CD. According to Rule 27, chord BA is parallel to line segment CD. Already known. Chord BA is parallel to line segment CD according to Rule 27. So in the next step, we will define the center of this circle. This point is point O, and from point O we will do perpendicular on line segment CD. And from point O, that is the center of this circle, we will do perpendicular on chord CD. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and line segment CD. This point is point M. In the next step, we will extend the perpendicular OM by straight line until it touches chord BA. Again, we will extend perpendicular OM by straight line until it touches chord BA. And we will define the touching point of the extended perpendicular OM with chord BA. This point is point M. We know that line segment CD is parallel to chord BA, and therefore the perpendicular OM, the extended perpendicular OM, must be parallel to chord BA. Again, because of the fact that CD is parallel to BA, the extended perpendicular OM must be parallel to chord BA also. That is to say, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the rule that I mentioned. So, in quadrilateral BCMN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 preceding angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees, and therefore this 4 preceding angle must be equal to 90 degrees in its size. So inside quadrilateral BCMN we have 4 right angles, and according to Rule 5, any quadrilateral that has 4 right angles must be at least right angle if not a square. So we invert to quadrilateral BC and M as a rectangle because it has 4 right angles. From the center of this circle, that is to say from this point O, we have perpendicular ON on chord BA. Again, from the center of this circle to this point O, we have perpendicular ON on chord BA. According to Rule 19, the perpendicular ON that is drawn from the center of this circle that is to say from point O bisect chord BA. So, repeat Rule 19. According to Rule 19, the perpendicular from the center of a circle towards any chord bisect the chord. In the morning we have a circle, point O is the center of this circle. From point O we have perpendicular OM on chord AB. And from point O we have perpendicular OM on chord AB. And according to this Rule 19, the perpendicular OM bisect chord AB. If OM bisects chord AB, it means that AM equals to MB. We can actually implement Rule 19 in our drawing. Why? Because in our drawing, we have from the center of this circle that is to say from point O, we have perpendicular ON on chord BA. We have perpendicular ON on chord BA. And according to Rule 19, perpendicular ON bisect chord BA. BA in total equals to 13. Therefore, the first half BN must be equal to 13 over 2, that is 6.5. And the second half of BA, that is NA, must be also equal to 6.5 units in its length, according to Rule 19, of course. So we have already found out that quadrilateral, this is quadrilateral BCMN, that is a rectangle, but we also know that the opposite sides of a rectangle are equal to each other. So in rectangle BCMN, side BN must be equal to the opposite side CM, but BN equals to 6.5, therefore the opposite side BM must be also equal to 6.5 units in its length. ON is a perpendicular, it is absolutely a straight line. So if you focus on the lower side of the straight line ON and point M, here the sum of the angles must be equal to 180 degrees according to Rule 3. Rule 3 says that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the lower side of the straight line ON and point M? We have this angle that is a right angle according to our construction, plus this missing angle. In total the sum of those two angles must be equal to 180 degrees according to Rule 3. Therefore, this missing angle must be equal to 90 degrees in its size. In the next step, we will do a construction. That is to say, from point A, we will do perpendicular on line 7 CD. Again, from point A, we will do perpendicular on line 7 CD. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and line 7 CD, this point L. By doing this construction, we get the lower quadrilateral MNLA. In the lower quadrilateral MNLA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this fourth missing angle must be equal to 90 degrees in its size. So in quadrilateral NMLA we have 4 right angles. So according to Rule 5, quadrilateral MNLA is rectangle because it has 4 right angles. So I write it down. The lower quadrilateral MNLA is rectangle according to Rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in the lower rectangle MNNA, side NA must be equal to the opposite side ML. But NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. What is the length of this line segment LD? From the drawing it is very easy to see that LD in total equals to CD minus CL. Again, CD minus CL equals to LD. So write it down. LD equals to CD minus CL. So LD in total equals to CD. CD equals to 18 units in its length, according to what is given as the question. Minus CL. CL in total equals to 6.5 plus 6.5, that is 13. So in total we should find out that LD equals to 13, to 18 minus 13, that is 5. LD equals to 5 units in its length. This is the short line segment LD, that is equals to 5 units in its length. In the next step, we will extend line segment DC by side line until it touches the circle. And when you find the touching point of the extended line segment DC with this circle, this point is point T. By doing this construction, you can do chord TD. This is chord TD, and we have perpendicular OM bisects chord TD according to rule 19. Again, perpendicular OM that is drawn from the center of the circle bisects chord TD. That is to say, TM equals to MD according to rule 19. So write it down. According to rule 19, TM equals to MD. TM equals to MD according to rule 19. MD in total equals to 6.5 plus 5. 6.5 plus 5 is 11.5. So we can write here that MD equals to 11.5. And from this equation, TM equals to MD equals to 11.5. We will derive that TM also equals to 11.5 units in its length. TM equals to 11.5. This is line segment TM that is equals to 11.5 units in its length. Again, this is line segment TM that is equals to 11.5. So from one side, TM equals to 11.5, but from the other side, TM equals to TC plus CM. From the other side, TM equals to TC plus CM. So 11.5 equals to TM, and TM equals to TC. TC is the missing side, so we leave it as it is. TC is the missing side, plus CM. CM equals to 6.5. From this equation, we derive that 11.5 equals to TC plus 6.5. 11.5 equals to TC plus 6.5. Here we subtract 6.5 from this equation, and we get that TC, the missing side TC, is equal to 11.5 minus 6.5 is 5. So here, this is 970 TC, this is equal to 5 units in its length. TC equals to 5 units in its length. In the next step, we will do construction, that is to say, we will extend 970 BC by a straight line until it touches the circle. And we will define the touching point of the extended 970 BC with this circle. This point is point Q. By doing this construction, we created here called BQ. This is called BQ. That intersects with chord TD at point C. Again, chord BQ intersects with chord TD at point C. So here we can implement rule 15. Repeat quickly on rule 15. According to rule 15, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. In the domain we have a circle. This is called AB that intersects with chord CD at point O. So in this moment the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. We can definitely implement rule 15 in our drawing. Why? Because in our drawing, chord TD intersects with chord BQ at point C. So it is now in our original drawing. Chord TD intersects with chord BQ at point C. So all the requirements of rule 15 are satisfied, and therefore we can implement rule 15. According to rule 15, the following equation is true, that TC times CD equals to BC times CQ. Again, TC times CD equals to BC times CQ. TC times CD equals to BC times CQ according to rule 15. This equation is the implementation of rule 15 in our drawing. TC is 5 times CD. CD equals to 18 units in itself according to what is the last equation. And it is equals to BC. BC 6 times CQ. CQ is the missing side, so leave it as it is. So in total we should find out that 5 times 18 equals to 6 times CQ. Here we divide this equation by 6, and we get that 18 over 6 is 3, and 3 times 5 is 15. So CQ equals to 15 units in its length. This is 97 CQ, that is equals to 15 units in its length. In the next step, we will join points Q and A together by straight line. We join points Q and A together by straight line. By doing this construction, we actually render there peripheral angle ABQ. This is peripheral angle ABQ, that is equal to 90 degrees in its size, and peripheral angle ABQ subtend on chord QA. Again, peripheral angle ABQ subtend on chord QA. So we can implement here rule 5. Repeat quickly rule 5. According to rule 5, any peripheral angle that is equal to 90 degrees in its size must subtend on the diameter of the circle. In the drawing, we have a circle. This is peripheral angle MAN that is equal to 90 degrees in its size, and therefore, according to this rule 5, peripheral angle MAN, that is the right angle, must subtend on the diameter of this circle. And indeed, peripheral angle MAN subtend on MN, that is the diameter of this circle. So according to this rule 5, any peripheral angle that is equal to 90 degrees in size must subtend on the diameter of the circle. We can definitely implement rule 5 in our drawing. One to the normal drawing, we have peripheral angle ABQ that is equal to 90 degrees in its size, and therefore, according to rule 5, peripheral angle ABQ, that is the right angle, must subtend on the diameter of the circle. Peripheral angle ABQ subtend on chord QA, and therefore, according to rule 5, chord QA must be the diameter of the circle. So it is done. If you found out that according to rule 5, chord QA is the diameter of the circle. The diameter of the circle is twice as long as the radius. If the radius of this circle is r, then the diameter QA must be equal to 2r. That is to say, the diameter QA equals to 2r. In the next step, I'll copy the right triangle ABQ in a new page, and we will implement on this right triangle ABQ the Pythagoras theorem. Side BQ equals to 6 plus 15, that is 21. Side BA equals to 13 units in its length according to what is given as the equation. And the hypotenuse AQ is the diameter of the circle, that is equal to 2r. So copy the right triangle ABQ in a new page, and we will implement the Pythagoras theorem on this right triangle ABQ. Here by PT is the abbreviation for Pythagoras theorem. So actually, this is the right triangle ABQ that according from the original drawing. According to the Pythagoras theorem, in this right triangle ABQ, QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. So I write it down. QA squared, that is the square of the hypotenuse, is equal to to QA squared, that is the square of the hypotenuse, equals to QB squared plus BA squared. QA is 2R, therefore QA squared is 2R squared, that is 4R squared, and it is equal to QB squared. QB is 21, QB is 21, therefore QB squared is 21 squared, that is 441 plus BA squared. BA is 13, therefore BA squared is 13 squared, that is 169. So in total, we found out that 4R squared equals to 441 plus 169. So 4R squared equals to 441 plus 169 is 610. So in total, we found out that 4R squared is equal to 610. Here we divide this equation by 4 and we get that R squared equals to 610 over 4 is equal to 152.5. So R squared equals to 152.5. Our task is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Therefore, the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared, so it is pi r squared. The area of our circle must be equal to pi r squared. But r squared is 152.5. So we substitute r squared by 152.5 and get that the area of our circle is equal to pi times 152.5 square units in its size, or in terms of numbers, this expression pi times 152.5 is equal to 479.09 square units in its size. So we found out that the area of this circle, that is the area that we are looking for this question, it is equal to either 152.5 pi square units in its size, or in terms of numbers, the area of this circle is equal to 479.09 square units in its size. So we finish with the first method. In the next step, I will present to you how to find out the area of this circle according to the second method. In the second method, we use with the data that we already obtained from the second method. In the second method, we already found out that line 7CQ equals to 15. This is line 7TC, that is equals to 5. So we use this data in the second method. So here we can implement rule 26. Why? Because we have chord TD that intersects with chord BQ at 90 degrees at point C. Whenever you have two chords that intersect with each other at 90 degrees, you can implement rule 26. So I repeat quickly on rule 26. According to rule 26 is true in any circle. If two chords, that is to say A, B, and C, D, intersect with each other at a right angle, they intersect with each other at 90 degrees. They create an intersection point 90 degrees with each other at point O, that is their intersection point. So if two chords intersect with each other at 90 degrees, exactly according to this drawing, then in this drawing the following equation will be true, that AO square plus OB square plus CO square plus OD square equals to 4R square, and R is the radius of the circle. So if chord AB intersects with chord CD at 90 degrees, that is to say the intersection point they create with each other 90 degrees, and then the intersection point occurs at point O, then the following equation will be true, that AO square plus OB square equals to CO square plus OD square. So we can definitely implement Rule 26 in our drawing. Well, as I mentioned before, chord TD intersection chord BQ at 90 degrees, at point C. So all the requirements for Rule 26 are satisfied, and therefore we can implement in our drawing Rule 26. So if you're done, if you found out that in our original drawing, chord TD intersects with chord BQ at 90 degrees. And the intersection point occurs at point C. Repeat again. Now, original drawing, chord TD intersects with chord BQ at 90 degrees, and the intersection point occurs at point C. So all the requirements of Rule 26 are satisfied, and therefore we can implement Rule 26 in our drawing. According to Rule 26, the following equation will be true: that TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. And R is the radius of the circle. Then again, according to Rule 26, the following equation will be true: that TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared, and R is the radius of the circle. Repeat again, according to Rule 26, now drawing the following equation will be true: that TC squared plus CD squared plus BC squared plus CQ squared equals to 4R squared. TC is 5, therefore TC squared is 5 squared, that is 25, plus CD squared. CD is 18, therefore CD squared is 18 squared, that is 324, plus BC squared. BC is 6, therefore BC squared is 6 squared, that is 36, plus CQ squared. CQ is 15, therefore CQ squared is 15 squared, that is 225. And it is equal to 4R squared. So if you found out that according to Rule 26, +25 plus 324 plus 36 plus 225 equals to 4R squared. 25 plus 225 is 250. So 250, and we have 324 plus 36, that is 360. So 250 plus 360 equals to 4R squared. 350 plus 600, 250 plus 600, 250 plus 360 is 610. That is equal to 4R squared. Here we divide this equation by 4, and we get that R squared equals to 610 over 4 is 152.5. So if you found out that R squared equals to 152.5, our task is to find out the area of this circle. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. And again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of our circle must be equal to pi times the radius of our circle squared, and the radius of our circle squared is r squared. So in total, the area of our circle must be equal to pi r squared. So it is pi times r squared, but r squared is 152.5, therefore we substitute r squared by 152.5, and we get that the area of our circle must be equal to either 152.5 pi square units in size, so in terms of numbers, it is equal to 479.09 square units in its size. Okay, again, we can find out in both methods that the area of this circle equals to either 152.5 pi square units in its size, or in terms of numbers, the area of this circle equals to 479.09 square units in its size. So we finish with the second method and the second question also. So in the next step, I'll summarize the lecture. I'll start with the first question, of course. In the first question, our task is to find out the radius of this circle. So, in the drawing, we have a circle, and this is the right triangle ABC. Side AB of the right triangle ABC equals to 4 units in its length. This is line segment AED, that is also equal to 4 units in its length. This is line segment DC, that is equal to 1 unit in its length. This is angle ABC, that is a right angle. And again, our task is to find out the radius of this circle. So here we can implement rule 25. If we focus on this common standpoint point C, on this common standpoint point C we have tangent CE, that is tangent to this circle is point E, and we also have secant CA that cuts the circle at 2 points D and A. So all the requirements of rule 25 are satisfied, and therefore can implement the rule 25. According to rule 25, the following equation is true, that CE squared equals to CD times CA. Again, CE squared equals to CD times CA. Okay, again, according to rule 25, the following equation is true. That CE squared equals to CD times CA. So CE is the missing tangent to electricity, so it is CE squared equals to CD. CD is 1 times CA. CA in total is 1 plus 3, that is 4. So in total, if you found out that CE squared equals to 1 times 4, that is 4. So CE squared equals to 4. We took out of this equation. If I found out that CE, the missing tangent CE is equal to 2 units in its length. CE equals to 2 units in its length. In the next step, I call it the right triangle ABC. In a new page, and we implemented the Pythagoras theorem. This right triangle ABC. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So this is the right triangle ABC that I call it from the original drawing. This right triangle ABC, according to the Pythagoras theorem, AC squared, that is the square of the hypotenuse, equals to AB squared plus BC squared. AC is 4, therefore AC squared is 4 squared, that is 16, and it is equals to AB squared. AB is 3, therefore AB squared is 3 squared, that is 9, plus BC squared. BC is the missing sign, so electricity. So in total, we found out that 16 equals to 9 plus BC squared. Here we subtracted 9 from this equation. If I found out that 16 minus 9 is 7, so 7 equals to BC squared. Here we took a root out of this equation. If I found out that the missing sign BC is equals to the square root of 7 units in its length. So this is the missing side. This is the missing side BC, that is equals to the square root of 7 units in its length. EC equals to 2. So what is the length of BE? BE equals to BC minus EC. Again, BE equals to BC minus EC. And again, BE equals to BC minus EC. BE equals to BC minus EC. So B equals to BC, that is square root of 7, minus EC, that is 2. So in total B equals to the square root of 7 minus 2 units in its length. In the next step, we join points O and D together by straight line. Point O is the center of the circle, point A is the point of the circle itself, therefore O is the radius of the circle. We define the radius of the circle itself, so O equals to R. The radius of E is equals to R, the radius of E is bound to point E, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius EO. If BC is perpendicular to EO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. When doing this construction, we get the quadrilateral ON, but in the next step, actually, we join points from point O, that is the center of this circle, we do perpendicular on AB. Again, from point O, we do perpendicular on AB. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AB. This point is point N. By doing this construction, we get the quadrilateral ONBE. In quadrilateral ONBE, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4 facing angle, in total they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 facing angle must be equal to 90 degrees in its side. So inside quadrilateral ONBE we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be this rectangle in front of the square. So we let quadrilateral ONBE is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle ONBE, side EB must be equal to the opposite side ON. But EB is square root of 7 minus 2, therefore the opposite side ON must be also equal to the square root of 7 minus 2 units in its length. Likewise, according to the sum rule, in the same rectangle ONBE, side OE must be equal to the opposite side NB. But OE is out, therefore the opposite side NB must be also equal to R. So NB equals to R, and AB equals to 3. Therefore, the missing 970 AN must be equal to AB minus NB. Again, AN must be equal to AB minus NB. So AN equals to AB, AB is 3 according to what is given in the question, minus NB, NB is R. So in total, AN equals to 3 minus R. In the next step, I copy the right grand triangle A and O in the new page. Actually, before that, we join points O and A together by straight line. Point O is the center of the circle, point A is the point of the circle itself, therefore OA is the radius of this circle, is equals to R. So in the next step, I copied the right hand triangle O and A in the new page and implemented the better law on this right triangle O and A. So actually, this is the right triangle A and O that I copied from the original drawing. This right triangle A and O according to the better theorem. AO squared, that is the square of the hypotenuse, equals to AN squared plus ON squared. AO is out, therefore AO squared is R squared, and it is equals to AN squared. AN is 3 minus R, therefore AN squared is 3 minus R squared, plus ON squared. ON is square root of 7 minus 2, therefore ON squared is square root of 7 minus 2 squared, that is square root of 7 minus 2 squared. So in total, we actually found out that R squared equals to 3 minus R squared plus square root of 7 minus 2 squared. So R squared equals to 3 minus R squared. 3 minus R squared equals to 3 squared, that is 9, plus R squared, that is plus R squared, minus 2 times 3 times R, that is minus 6R, and square root of 7 minus 2 squared is 0.417. So in total, we found out that R squared equals to 9 plus R squared minus 6R, plus 0.417. Here we have R squared on both sides of the equation. This equation, so R square will get cancelled, R square cancels R square, and this side of the equation will be left with nothing, that is to say 0, while in the other side of this equation we have 9 minus 6R. 9 minus 6R plus 0.417. 9 plus 0.417 equals to 9.417 minus 6R. So in total, we actually found out that 0 equals to 9.417 minus 6R. Here we added 6 out of this equation, if we found out that 6R equals to 9.417. Here we divided this equation by 6 and finally found out that the radius of this circle, that is the radius that we are looking for this question, is equal to 9.417 over 6, that is 1.57 units in its length. I repeat again, we found out that the radius of this circle R equals to 1.57 units in its length. We finish with the first question. In the next step, I presented you the second question, and we solved the second question in two different methods. Our task in the first question is to find out the area of this circle. So in the drawing, we have a circle. This is 97 BC, that is equals to 6 units in its length. This is called BA, that is equals to 13 units in its length. This is line 7 CD, that is equals to 18 units in its length. This is angle ABC, that is right angle. This is angle BCD, that is also right angle. Again, our task is to find out the area of this circle. First of all, those two angles are defined as one-sided. Those two angles are defined as one-sided interangles, and they are located between line BA and line CD. And because of the fact that the sum of those two one-sided interangles is equal to 180 degrees, they must be located between parallel lines. That is to say, chord BA is parallel to line 7 CD according to rule 27. Again, according to rule 27, chord BA is parallel to line 7 CD. In the next step, you find the center of this circle. This point is point O. And then we joined from point O, we do perpendicular on CD. Again, from point O, we do perpendicular on line 7 CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and line 7 CD. This point is point M. In the next step, we extended the perpendicular OM by a straight line until it touches chord BA. We define the touching point of the extended perpendicular OM with chord BA. This point is point N. And because of the fact that according to rule 27, chord BA is parallel to line 7 CD, the perpendicular to CD, the extended perpendicular to chord CD must be also perpendicular to chord BA. Again, the perpendicular to line 7 CD, that is OM, the extended perpendicular OM must be also perpendicular to chord BA. Why? Because they are parallel to each other. So actually this angle equals to 90 degrees, and this angle also equals to 90 degrees according to the rule that I mentioned. So here we have, so this angle equals to 90 degrees, and this angle equals to 90 degrees, according to the rule that I mentioned. If we focus on the lower side, ON is a perpendicular, it is absolutely a straight line. So if we focus on the lower side of the straight line ON and point M, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of the straight line is equal to 180 degrees. So which angles we have at the lower side of the straight line ON at point M? We have this angle that is right angle plus this missing angle. In total it must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. Likewise, at the upper side of the straight line ON at point M, The sum of the areas must be equal to 180 degrees according to all three. So which areas we have at the upper side of the third line ON at point M? We have this angle that is the right angle according to our construction, plus this missing angle. In total they must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees inside. So in conclusion, we found out that those two angles are both right angles. So inside quadrilateral BCMN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So actually we have here 4 right angles, because those two angles are right angles according to what is given in the equation. This angle is a right angle according to the rule that I mentioned, that the perpendicular to CD must be also perpendicular to BA. So this angle is right angle, and this angle is right angle according to rule 3. So in quadrilateral BCMN we have 4 right angles, and therefore quadrilateral BCMN is right angle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle BCMN, side BN must be equal to the opposite side CN. But before that, you can implement here rule 19. According to rule 19, the perpendicular ON from the center of the circle, that is to say from point O, bisects chord BA. Again, the perpendicular ON bisects chord BA. But BA is in total is 13, therefore each half must be equal to 13 over 2, that is 6.5. The first half BN is 6.5, and the second half NA is also equals to 6.5 units in its length. So in rectangle BCMN, side BN must be equal to the opposite side CM, but BN is 6.5, therefore the opposite side CM must be also equal to 6.5 units in its length. In the next step we did another construction, that is to say from point A we do perpendicular on CD. Again from point A we do perpendicular on CD. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and side CD. This point is point L. By doing this construction, we get the quadrilateral MNLA. Inside quadrilateral MNLA, we have 1, 2, 3, 4 right angles. We already found out that this angle is equal to 90 degrees according to rule 3. This angle is equal to 90 degrees according to what I already explained. And this angle equals to 90 degrees according to our construction. So actually in quadrilateral MNLA we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 missing angle, in total they must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4 missing angle must be equal to 90 degrees in its size. So inside the quadrilateral MNLA we have 4 right angles, and therefore according to rule 5, quadrilateral MNLA is a rectangle, because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle MNLA, side NA must be equal to the opposite side ML. But NA is 6.5, therefore the opposite side ML must be also equal to 6.5 units in its length. So what is the length of this missing line segment LD? From the drawing it is very easy to see that LD in total equals to CD minus CL. Again, CD minus CL equals to LD. Repeat again, LD equals to CD minus CL. So LD equals to CD, that is 18, according to what is given in the question, minus CL. CL in total equals to 6.5 plus 6.5. CL in total equals to 6.5 plus 6.5, that is 13. So in total LD equals to 18 minus 13, that is 5. This short line segment LD equals to 5 units in its length. In the next step, we extended line segment DC by straight line until it touches the circle. We define the touching point of the extended line segment DC with this circle. This point is point T. By doing this construction, we created a chord TD. This is chord TD, and we have from the center of this circle, that is to say from point O, we have perpendicular OM on chord TD. Again, we have perpendicular OM on chord TD. And according to rule 19, perpendicular OM that is on from the center of this circle, that is to say from point O, perpendicular OM bisects chord TD. If OM bisects chord TD, it means that TM equals to MD. According to rule 19, Tm equals to Md. But Md in total equals to 6.5, that is 6.5 plus 5, that is 11.5. So Md equals to 11.5, and from this equation, Tm equals to Md equals to 11.5, we derive that Tm also equals to 11.5 units in its length. This is 97 Tm, that is equal to 11.5 units in its length. So from one side, Tm equals to 11.5, but from the other side, Tm also equals to Tc plus Cm. Again, Tm equals to Tc plus Cm. Tc plus Cm. So from the other side, Tm also equals to Tc plus Cm. So 11.5 equals to Tm, and Tm equals to Tc plus Cm. But Cm is 6.5. So substitute Cm by 6.5, and in total we found that 11.5 equals to, from this equation we derive that 11.5 equals to Tc plus 6.5. 11.5 equals to Tc plus 6.5. Here we subtract 6.5 from this equation, and we found out that Tc equals to 11.5 plus 6.5 is 5. So this is the missing 9 segment Tc, that is equals to 5 units in its length. In the next step, we extended line segment BC by straight line until it touches the circle. We define the touching point of the extended line segment BC with this circle. This point is point Q. By doing this construction, we created chord BQ. Chord BQ intersects with chord TD at point C. Again, chord BQ intersects with chord TD at point C. Therefore, we can implement here rule 15. Looking again. Chord TD intersects with chord BQ at point C. And therefore, we can implement here rule 15. According to rule 15, the following equation is true that Tc times Cd equals to Bc times Cq. Again, Tc times Cd equals to Bc times Cq. According to rule 15, Tc times Cd equals to Bc times Cq. Tc is 5 times Cd. Cd is 18, and it is equals to Bc, that is 6, times Cq, that is the missing side. So in total, we found out that 5 times 18 equals to 6 times Cq. Here we divided this equation by 6, and finally found out that Cq equals to 18 over 6 is 3, and 3 times 5 is 15. So in total, we actually found out that the length of line segment Cq is equal to 15 units in its length. In the next step, we join points A and Q together by straight line. When doing this construction, we can do preferential ABQ. This is equal to 90 degrees inside, and preferential angle ABQ subtend on chord QA. Again, preferential angle ABQ subtend on chord QA. And according to rule 5, any preferential angle that is equal to 90 degrees inside must subtend on the diameter of the circle. So preferential ABQ is equal to 90 degrees inside, and therefore it must subtend on the diameter of the circle. Preferential ABQ subtend on QA, and therefore according to rule 5, chord QA must be the diameter of the circle. Chord QA must be the diameter of the circle according to rule 5. QA is the diameter is twice as long as the radius. So if the radius is out, then the diameter must be equal to 2r. So QA equals to 2r. In the next step, I copied the right triangle ABQ in the new page, and we implemented the Pythagoras law on this right triangle ABQ. Actually, this is the right triangle ABQ, that is coming from the original drawing. AB equals to 14 units in its length. BQ equals to 6 plus 15, that is 21, and the hypotenuse QA is equal to 2r. It is also the diameter of the circle. The hypotenuse QA equals to 2r and BQ equals to 21. In this letter BQA, QA squared, that is the square of the hypotenuse, equals to BQ squared plus BA squared. QA is 2r, therefore QA squared is 4r squared, and it is equals to BQ squared. BQ is 21, therefore BQ squared is 21 squared, that is 441, plus BA squared. BA is 13, therefore BA squared is 13 squared, that is 169. So in total we should find out that 4r squared equals to 441 plus 169. So 4r squared equals to 441 plus 169 is 610. So 4r squared equals to 610. Here we divided this equation by 4 and find out that r squared equals to 610 over 4 is 152.5. So r squared equals to 152.5. Our task is to find out the area of this circle. Actually we know that the area of any circle equals to pi times the radius of the circle squared. And therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared. So in total the area of our circle must be equal to pi r squared. R squared is 152.5, therefore we substitute r squared in this expression by 152.5 and found out that the area of our circle must be equal to pi times 152.5 square units in its size. In terms of numbers, it is equal to 439.09 square units in its size. Repeat again, if you found out that the area of this circle must be equal to either 152.5 times pi square units in its size, or in terms of numbers, the area of this circle must be equal to 479.09 square units in its size. So we finish with the first method. In the next step I presented to you how to find out the area of the circle according to the second method. In the second method, we use before the phase that we only found out in the first method. That is to say, we only found out in the first method that line 7TC equals to 5 units in its length, and line 7CQ equals to 15 units in its length. So use the data from the first method, this data in the second method. So here we can implement rule 26 in our drawing. Why? Because we have chord TD that intercepts with chord BQ at 90 degrees at point C. Whenever you have two chords that intersect with each other at a right angle, you can implement rule 26. So repeat quickly on rule 26. According to rule 26 is true in any circle. So in any circle with two chords, A, B and CD intersect with each other at a right angle, chord AB intersects with chord CD at right angle. They create between them 90 degrees at their intersection point, which is point O. So in this moment the following equation is true that AO square plus BO square plus CO square plus DO square equals to 4R square, and R is the radius of the circle. We can definitely implement rule 26 in our drawing because we have chord TD that intersects with chord BQ at 90 degrees at point C. So all the requirements of rule 26 are satisfied, and therefore we can implement rule 26. According to rule 26, the following equation is true that TC square plus CD square plus BC square plus CQ square equals to 4R square. Repeat again, according to rule 26, the following equation is true because of the fact that chord TD intersects with chord BQ at 90 degrees at point C. The following equation will be true according to rule 26. TC square plus CD square plus BC square plus CQ square equals to 4R square, and R is the radius of the circle. This equation is the implementation of rule 26 in our drawing. TC is 5, therefore TC square is 5 square, that is 25, plus CD square. CD is 18, therefore CD square is 18 square, that is 324, plus BC square. BC is 6, therefore BC square is 6 square, that is 36, plus CQ square. CQ is 15, therefore CQ square is 15 square, that is 225, that is equals to 4R square. 25 plus 225 is 250, and 324 plus 36 is 360. is equals to 4 r squared. So 250 plus 360 equals to 4 r squared. 250 plus 360 is 610, so 610 equals to 4 r squared. Here we divided the equation by 4 and found out that r squared equals to 610 over 4 is 152.5. So r squared equals to 152.5. Our test is to find out the area of this circle. Actually, we know that the area of any circle equals to pi times the radius of the circle squared, and therefore the area of our circle must be equal to pi times the radius of our circle squared. The radius of our circle squared is r squared, so the area of our circle must be equal to pi r squared. But r squared is 152.5, so substitute r squared in this expression by 152.5, and we found out that the area of our circle must be equal to either 152.5 pi square unit in size, or in terms of numbers, the area of our circle must be equal to 479.09 square unit in size. So in both methods, we arrive to the same result. We arrive to the result that the area of this circle must be equal to either 152.5 times pi square unit in size, or in terms of numbers, the area of this circle must be equal to 479.09 square unit in its size. Okay, thank you very much.